highly specialized dummy. You ever feel that way? Want to figure out the net force. And it's complicated because all the motions that's going on, but it's actually simple too. So we can do this initial just estimation of the net force because we know the dummy's initial speed. His initial speed is equal to 0. We also know, or we can sort of estimate his final speed because as this car travels along, there's the car. It's traveling at 40 kilometers per hour. And then you have this guy standing in front of it. The guy is going to go up to the speed of the car. When the car hits him, he's going to take him from 0 up to 40 kilometers per hour. So our final speed of our dummy, at least an estimate, a decent estimate, is going to be 40 kilometers per hour. Now, we don't know the time over which it occurred, but we can just make an estimate for the time. The guys at the lab, they know. It said that the 30 milliseconds isn't the time for the collision. That was the time that they released the dummy just prior to being hit by the car. But let's just make an estimate. We'll say, I don't know, 1/10 of a second. It's not very long for the car to strike the dummy and for him to get up to that speed of 40 kilometers per hour. So we'll just say 1/10 of a second. We need to convert this to meters per second. In 1 kilometer, there are 1,000 meters, and in 1 hour, there are 3,600 seconds. And that is 40,000 over 4,000. It's about 10. We'll just call it 10 meters per second. Approximately. So we're going from about, is that right? 10 meters per second? I think that's right. 40,000. Okay, yeah, we'll just call it 10. And we'll call our time as 1/10 of a second. Now we also need to know the mass of the dummy. And a typical person is about 70 kilograms, so we'll say that he's about 70 kilograms. Now, to figure out the force, we say our force is our change in momentum divided by our change in time. This is always going to be true regardless of the type of collision that you have. Whether it's conservative forces or non-conservative forces, this will always be true, that our net force will equal to the change in momentum over the change in time. So that's going to be 70 kilograms times our change in speed, which is going to be 10 meters per second minus 0, divided by 0.1 seconds. So that is 700 over 0.1, which is going to be 7,000 newtons. And that's 7,000 newtons, acting on your knee. That's about 10 people sitting on your knee in just a matter of 1/10 of a second. So it's a big force to be acting on your knee. All right, let's try this problem. Actually, before we do that, I wanted to show you something. This is an aside, but I know that many of you are biology majors. Most of you are, and just want to tell you about a program. Hopefully your advisor has told you about this, but it's called the REU program. Do you guys know what I'm talking about when I say REU? Yes, no? It's the Research Experience for Undergraduates. It's funded by the NSF. Just going to Google NSF REU, the National Science Foundation REU. If you do that, let's see, it's the first thing that comes up. So you search for an REU site. And what these are research programs in the summertime. You go to a lab or you go to a major university, and they've applied for monies from the NSF to bring in students to do research with them. So they're usually big research groups that have a lot of different stuff going on. You go there for the summer. They pay you a reasonable salary, usually $4,000 or $5,000 for the summer. Usually they also pay for your housing and your travel. And you get to work with someone there that's an expert in their field. Often you'll get to go to conferences. Usually there are other students there from all over the country or even all over the world. It's a really great program, and especially if you're interested in going into research or going into graduate school of some sort, it's a great program to help you feel out what exactly you want to do when you graduate. So if you go here, you'll find lots of different topics. I did a couple when I was an undergrad in astronomy, and that just really helped me to feel out what it was that I wanted to study. But let's say you want to go into biology or chemistry or something like that. We'll do the biological sciences. I haven't looked at these, but let's see, they have lots of different sites. Like here's Alabama, or you can go to New York, or Kansas, or Idaho. All over the country you can go. We'll just pick on this one at, let's see, where do you want to go? Let's go to Boston College. So we'll go to this, they'll send you to their REU site, and then you can go there and you can find out what you need to do to apply. So if you want to take a look at that, REU for Research Experience for Undergrads, NSF, and you'll be able to apply on that on your own. Usually those applications are due in the early winter, January, February, March. So if you want to apply, you need to start thinking about it right now. Any questions about that? Oh yeah, okay. No problem. Any questions about the REU program? Now, if you're interested, come talk to me. I can tell you more about it. It's a great opportunity for you guys. All right, William. The weight of the vehicle is not relevant. Yeah, the force that acts on the object will cause the object to change motion, right? And so if we know the acceleration of the object, which is this basically, right? This is our change in velocity over our change in time, and this is the mass of our object, then the force required to cause this acceleration is going to be this 7,000 newtons. So we basically remove the car from the whole system. We're just looking at the object that we want to know what is the force that is acting on that object. Is that clear? That's a good question, because the next set of things that we'll look at, the conservation momentum, the mass of the car will be relevant. So you'll need to sort of figure out how to keep those separate in your mind. All right. I think it'll be easy once you see them, but let's do this quick test. Oh no, we've already done this one. Did we do this one? Yeah. Okay, so let's look at conservation of momentum. This says that in all collisions, the total momentum is conserved and it must not change. So for our system, it says that the initial momentum is equal to the final momentum. Remember, these are vector quantities. Sometimes you'll see this written in a different way. And in fact, in the OpenStax reading, which you'll have up this afternoon, they'll write it as P is equal to P prime. That's all they mean, is just that the momentum at one point is equal to the momentum at another point. I'm going to write it in this way, but they use a prime in your reading. I'm going to use the initial and final. This refers to the momentum in a system. So you need to figure out what is the system that we're talking about. And because we're going to be talking about collisions, that system will have two or more particles. Because you can't have a collision with just, one object. That doesn't really make any sense. So we'll only talk about collisions with two or more particles. And in fact, in this class, we'll only deal with two particles. It makes the calculations a lot simpler. We'll also only deal with one-dimensional collisions. 2D collisions is not that hard. And those of you doing the MCAT and stuff, I'll show you the beginnings of a 2D collision. But we're just going to cover 1D collisions in this class. Let's do an example. I have these two particles. They collide and they rebound. And I give you some of their information. I give you the mass of the particles here. This is my 3 kilogram. This is my 4 kilogram. They're traveling towards one another. This one is traveling at 1 meter per second. And this one is traveling with a speed of 2 meters per second. But remember, momentum is a vector quantity, so we have to remember the signs. I give you that here, but on the test, I'll probably just give you the magnitude, and you'll just have to pick which one is positive or negative. This one's moving to the right, so it's positive. This one's moving to the left, so it's negative. All right? Now, these two objects have a certain amount of momentum. I can calculate the momentum. I can say that the initial momentum here is M1 V1 initial plus M2 V2 initial. And that's going to be 3 times 1 plus 4 times negative 2. So the total momentum is going to be 3 minus 6, or negative 3 kilogram meters per second. That is the total momentum of this system. You can think about it, because think about this in terms of, I have two particles here that are both moving in opposite directions, but this is the bigger of the two particles, and it's also going at the bigger speed. So you might imagine that the momentum of this bigger particle is going to dominate the momentum and cause it to go in a negative direction. And that's why my momentum comes out as negative, because when I combine these two particles in a system, it tells me that the net momentum is in that direction. Because I have this bigger particle with a bigger speed, it just has more momentum in the negative direction. Yeah?
Shouldn't it be negative 5?
Yes. Thank you. Negative 5. All right, so I want to know, I also give you the final velocity of V1. I tell you that this speed is minus 5 meters per second. This is V1F. And I want to know what is the final velocity of the second particle. So the way you would do this is you would say P initial is equal to P final. That's going to be M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Now, we've already done the left-hand side of this and found the net momentum. It was negative 5, right? Is that right? Yeah, so it's negative 5, and then M1 is 3 kilograms times negative 5 meters per second plus 4 kilograms times V2F. And then I solved that for V2F. So that's 5 plus 8, that's 3 divided by 4 equals V2F. Let's see. Oh, no, I'm sorry. That's not right. It's negative 15, 10 divided by 4, which is 10 divided by 4, which is equal to 2.5. Okay? So you'll have two objects. They'll be moving in either the x or the y direction, and you can set their momenta equal to one another. Please?
How would you V1 is negative 5?
Oh, I gave V1F in the initial problem. So he asked, how do I know that V1F is negative 5? It's just given to you. In order to solve these, you have to know at least 3 of the particles, or at least you have to know 3 pieces of information: the initial velocities of the first 2 and one of the final velocities, or some combination of there. There can only be one unknown for your work. Does that answer your question? Yeah. All right. Let's try a different problem. You have some in your homework. Let's see, we're going to watch a video clip here. Doesn't really matter what his mass is. It's really only the ball and only his face. So we need to know a couple of things. First of all, what is the mass of the ball? What do you think for the mass of the ball in kilograms? Okay, yeah, maybe about 0.1. Yeah, we'll say 0.1 kilograms. Those dodgeballs aren't very heavy. We'll say 100 grams, like one of those little weights that you use upstairs that are about, I don't know, a ½ inch thick. So the mass of the ball is about 0.1 kilograms. We want to know what is the velocity of the ball initially. If you watch the clip, you'll see that right after it hits his head, it drops down. So his final velocity of the ball is equal to 0. Now we also want to know the mass of White Goodman. Let's see, I'll call it MW. Well, 70 kilograms is sort of a typical person, but you know, he's a pretty big guy, so we'll just say that he's about 100 kilograms. And then his initial velocity, what's his initial velocity? 0, right? He's just standing there. And then we need to make some assumptions about his final velocity. About how far back does he go? About 2 or maybe even 3 meters, and he does that in about 1 second. And in fact, it is about a second. So he goes back about, I'll say it's 3 meters. 3 meters in 1 second. So we'll just estimate it at about 3 meters per second, because he covers 3 meters in 1 second. That's not unreasonable. So now we want to figure out what is the velocity of the ball. I'll give you just a minute, so go ahead and try to calculate what is the velocity of the ball, and then I'll jump in about a minute. But what you're doing here is you're setting your initial momentum equal to your final momentum. Now in this case, one of your objects will have no initial momentum, and then the other object will have no final momentum. So you're setting one momentum equal to another, and then solving for the velocity of the ball. All right, so our initial momentum, our system consists of the ball and White Goodman. Initially, which one is 0, the ball or White Goodman? White Goodman, so we can get rid of that one. And then a final state, the ball or White Goodman? The ball, which comes to a velocity equal to 0. Let's see, this, which is right here. So the final velocity of the ball is 0, so it goes away, that final momentum. So we can say that the mass of the ball times the initial velocity of the ball is equal to the mass of White Goodman times the final velocity of White Goodman. And we solve this now for the initial velocity of the ball. What'd y'all get? 3,000, right? So that's going to be MW VFW divided by MB. 100 kilograms times 3 meters per second divided by 0.1 kilograms. And then this gives us the initial velocity of the ball. Notice my kilograms cancel. It gives me 3,000 meters per second. Just to give you a reference on what that is, I mean, the muzzle velocity of a handgun, any idea what that is? It's about 300 meters per second. So this is about 10 times the muzzle velocity of a handgun. It's pretty impressive, that Peter LaFleur, right? All right, let's try it. Try a clicker. Oh, look, here's the same problem, but with different numbers. So why don't you try this? I will zoom out. Here, with more realistic values for the velocity of the ball, what is the velocity then of White Goodman after you hit him? All right, let's stop about 140 or 145. About 145. It's about 8 more seconds. Just guess if you're not sure. 145. Okay, A is right. We do work this exactly the same way, except now we're looking for a different unknown. Our initial momentum is only for the ball. Our final momentum is only for White-Goodman. Those are the only two particles in our system. So we set those two equal to one another. We say that the mass of the ball times the initial velocity of the ball is equal to the mass of White-Goodman times the final velocity of White-Goodman. Now remember, I'm leaving two terms out here. I'm not writing them, but I have another term over here, which is the initial momentum of White-Goodman, but it's 0. And over here, I'm leaving out another term, which is the final momentum of the ball, which also goes to 0. And then I can put in some values here. The mass of the ball, I said, was 0.5 kilograms. He throws it at about 10 meters per second. So that's about 20 miles an hour or so. White-Goodman is 100 kilograms. And his velocity, VFW, is going to be 5 over 100, or 0.05 meters per second. So that's the answer. Let's do a few more clicker questions, please. Did we do this one? I think we started to do it, but let's do it anyway. I'm not sure if y'all saw the answer or not, but let's try this one out. Here you have a cart that rolls along. Rain falls into the cart, and we want to know what happens to the cart, to the speed of the cart. Does it speed up? Does it maintain constant speed, slow down, or does it stop immediately? It's also important that the rain falls vertically into the box. I'll tell you why. All right, let's stop at 55. Just a few more seconds. A few more seconds. Okay, good. C is right. Had we done this problem before? Had you already seen it? Yeah, some of you have. So the answer is C. But the reason it's C is because, well, the momentum here is constant. And I also know that the momentum is equal to m times v. So if m goes up, as it is, then v is going down. It's important, too, that the rain falls vertically into the box, because if it goes in horizontally, that would add momentum in the horizontal direction. So it's traveling along. There are no forces acting upon it. Since there are no forces acting upon it, F is equal to delta P delta T. Since this equals 0, that leads us to this conclusion. If there are no forces acting on an object, then the momentum doesn't change, because its speed doesn't change. But in this case, the mass is changing, as we can have. And if the mass changes, it goes up, that means the speed has to go down. Did anybody go to the play this weekend? No, it was really great. We went yesterday. It was hilarious. Did y'all go? No, it was very funny. All right. A system of particles is known to have a kinetic energy of 0. What can you say about the total momentum of the system? Positive, negative, 0, or you just can't say anything about the momentum. You don't know anything necessarily. I'll stop at 40. Okay, awesome. C is right. I think we had a very similar, maybe an identical question here. But if the kinetic energy is 0, that means the particles aren't moving. Right? And if the particles aren't moving, then they have no momentum. What do you call a cow with 2 legs? You say, I don't know. Lean beef. Okay, a system of particles is known to have a total momentum of 0. Does it necessarily follow that the kinetic energy is also 0? So before the kinetic energy was 0, but here the momentum is 0. Does that mean that the kinetic energy is 0? When the kinetic energy was 0, it did mean that the momentum had to be 0. But is the reverse true? All right, I'm going to stop at 40. Just a couple more seconds. Okay, good. It doesn't mean that the kinetic energy has to be 0, because I can have a system where I have one mass moving in this direction and another mass with equal mass and equal but opposite velocity. The momentum of this system is 0, even though the objects are moving, but the energy of the system, the kinetic energy of the system, is not 0. It's something more than 0. So I can have a system of particles whose net momentum is 0, but the kinetic energy is bigger than 0. Two objects are known to have the same momentum. Do they necessarily have the same kinetic energy? If two objects have the same momentum, does that mean they also have the same kinetic energy? All right, I'm going to stop at 30. Bless you. Okay, very good. So they don't necessarily have to have the same momentum and kinetic energy, because P is equal to M times V, and kinetic energy is 1/2 mv squared. And so I can have a different mass and velocity, and because I have this squared here, it will give us a different kinetic energy. We'll see that come up later, that if I have something moving at a bigger speed, then it's going to have a lot more kinetic energy, even if they have the same masses, because the speed is squared. Oh, what type of songs do planets like to sing? Neptunes. Okay. Force acts on a 100 kilogram boulder. The same force acts on a 130 gram pebble. How does the rate of change of the momentum compare for the boulder and pebble? All right, I'm going to stop at 55, 55. Feel free to ask your neighbor. Y'all sort of split on the answer, and that's okay, though. I'll show you. Okay, let's see. C is right. You want to think about this expression that we have. We really have a couple of things, a couple of expressions, and this is one of them that you'll need to know, is that F is equal to delta P over delta T. That if I have a force on an object, it changes its momentum. Right? This is just Newton's second law. If I apply a force to an object, I change its momentum. Here I'm applying a force of 200 newtons to two objects, the same force, 200 newtons. And I'm asking about the rate of change of their momentum. This is the rate of change of momentum. So if I have 200 newtons here, this is going to be the same for both objects. Now the objects aren't going to respond the same to that force because one's big mass and one's a small mass, but they'll both experience the same change in momentum. So C is the right answer here because I have this net force acting on two objects, changing their momentum in the same way. Okay, similar situation. How does the rate of change of the boulder's velocity compare to the rate of change of the pebble's velocity? Will the boulder change velocity at a faster rate than the pebble, a slower rate than the pebble, or the same rate as the pebble? All right, let's stop at 50. Okay, good. Right, that's right. So you have this force acting on a boulder. It has a bigger mass, so it's kind of a smaller acceleration. So I can think of it just in terms of Newton's second law, F equals ma. If m is big, a is going to be small. You kick the boulder, it hardly moves at all. You kick the pebble and it flies across the land. Small car and a large truck collide head-on and stick together. Which one has the larger momentum change? Think about this in terms of Newton's laws. I have this big object and a small object, and they collide, and they both experience a change in momentum. But which one will experience the larger? Or do they have the same? I'm going to stop at 52. 52. So a few more seconds, so get in your answers. Hey, very good. They both have the same momentum change. That's nice because you think of Newton's third law, right? Newton's third law says that this car exerts a force onto this truck, and this truck exerts the exact same force back on that car. It's an action-reaction pair. But if they exert the same force on one another, since force is delta P over delta T, it both also occurs in the same amount of time, then they're also going to experience the same change in momentum. Sometimes these questions are intuitive, sometimes they're not, like with this one. You have to read carefully and think about the forces that are involved, and also think how that's related to our change in momentum. Two boxes, one heavier than the other, are initially at rest. The same constant force acts on each one for exactly 1 second. Which box has more momentum after the force acts? Y'all can see? Yeah, you can see that. Okay, doing sort of okay. There's still about 20 of you that don't have the right answer. Ask your neighbor if you like. And remember, I have a force that's acting on two different objects, the same force for the same amount of time. And I want to know which box then has more momentum after the force acts. I'm going to stop at 105. 105. Okay, good. C is right. Again, because F equals delta P, delta T. I want to know which one has more momentum, has a bigger change in momentum. but they both have the same force that acts over the same amount of time, so my change in momentum will be the same for both. In the previous question, which box has the larger velocity? This force acts on a heavy box and a light box. Which one has the larger velocity after this force acts? They both have the same amount of momentum, we've already seen. Which one has the larger velocity, or both the same? Or we'll stop at 30? 30? I'll go to 32. Awesome. B is right. Hey, when do astronauts like to eat lunch? Are y'all hungry? I'm hungry. Oh, launch time. Okay, so this is like the pebble and the boulder. If you exert a force on the big thing, it'll have small acceleration. On the small thing, it'll have big acceleration. Let's try this. Small beanbag and a bouncy rubber ball are bounced from the same height above the floor. They both have the same mass. Which one will impart the greater impulse? Remember, the impulse is the change in momentum. Impulse is change in momentum. They're both vector quantities. All right, we'll stop at 55. All right, so B is right. This came up with the collision in the wall, but the answer here is the rubber ball. And the reason is that this delta P is P final minus P initial. All right, that's what the delta means, final minus initial. And so since the mass doesn't change, it's going to be M times VF minus VI. And what we want to think about is we have this ball. It initially has a speed that's downwards, and then in the final state, it comes back up again. So the way I'm going to write this, let's say that VI is negative 2 meters per second, and VF is let's say it's also 2 meters per second. But notice that it's positive while the initial is negative. And so my change in speed is going to be 2 meters per second minus negative 2 meters per second. So I'm going to have a change in speed of 4 meters per second total because it changes direction. Hey, y'all ever pop people in the behind with a wet towel? Y'all do that? I'm not sure that you're supposed to, but when I went to a boarding school in high school, and you put a bunch of 16, 17-year-old boys in the same dorm, and that's what they do. And we would go to great lengths to figure out what hurts the most. And what you do is, you know, ever heard of a rat tail? You take a towel, and it's like a damp towel, and it's a little damp, and then you roll it up just right, like you fold it over and you roll it up. And then you have this towel that really hurts. Like it will leave a mark on you if you hit it just right. And you go, and the art to hitting somebody with a rat tail is that you come and you fling it, and then you do what? You snap it, you pull it back. And it's the same idea here. That when you snap it, it pulls it back, and you get this recoil velocity. It just imparts a greater impulse and causes a greater force to act on their leg or wherever you're hitting them. Okay? So that recoil is pretty important for giving you maximal pain. All right. We'll do this one. This one's a similar idea. You're in a rainstorm, turns to hail, but you still have the same number of drops that land on your umbrella, except it was rain before, and now it's little pieces of ice. Same mass, same number, same speed. But which case requires more force to hold the umbrella? we'll stop at 50 or 48. 48. 5 more seconds. Okay, very good. Why, when it's hailing, why does that require more force? What happens to the hail that doesn't happen to the rain? It bounces off of your umbrella, right? Whereas the rain will fall onto your umbrella and then it just rolls off. So that the hail imparts a greater force, a lot like, you know, the rat tail, a lot like the bouncy ball. Bowling ball and a ping pong ball are rolling towards you with the same momentum. You exert the same force to stop each one, which takes a longer time to bring to rest. And I'm just going to remind you of the expression that we're dealing with, F equals delta P over delta T. All right, we'll stop at 42. 42. All right. B is right. This. Oh no. Okay, that's right. Yeah, because they have the same momentum. And they have the same force, so they're also going to have the same change in time. But you might not get this one, but it's pretty good. A neutrino walks into a bar, and he keeps on going. A neutrino, because neutrinos don't interact with matter, and so he walks into a bar, and then he just keeps on going. All right. We'll just do a few more. All right, so a box slides with an initial velocity of 10 meters per second, and then it collides inelastically. We'll get to this next time, but what that means is they stick together. So I have this object that travels along, and then it sticks to this thing, and I want to know what is the new speed. This is just like our conservation of momentum. It has a certain amount of momentum here, this block moving this speed, and now it has a certain amount of momentum here. These two blocks moving this speed. We'll deal with this more next time, but it works out exactly the same. All right, let's stop at 55. 55. Okay, awesome. E is right. My initial momentum is mvi. I understand you are itching to get out, but give me just a second more. M times vi, and then the final momentum is going to be 2m times vf, only because the two are sticking together now, and they're both moving. So the m's cancel here, and so vi is going to be 2 times vf. VI was 10, so VF is E. Is that what y'all put? Yeah. All right, we'll call it quits there. We'll wrap this up. But hey, listen, we're done with Chapter 5. We're almost done with Chapter 6. So make sure that you're up on those, because the exam is not that far away. Like next time, we'll wrap up Chapter 6.